work the true nature of gravity. I was going to start the proceedings tonight with a gravity joke, but I didn't think anyone would fall for it. So instead, I thought I'd start with a cartoon. So the first law of cartoon physics is gravity does not work until you look down. All very familiar with this. So this is true in the animated world, but in the real world, things operate quite differently. So gravity. Intuitively, gravity is the force that pulls everything to the ground, keeps planets in orbit around the sun, stars in orbit around galaxies. But is gravity really a force at all? This is what we'll be exploring tonight. So we'll go back to ancient times to see how the ancients perceived gravity. So the great Greek philosopher Aristotle, he believed that everything was made of four elements. We had earth, water, air, and fire, and everything was made up of those four elements. And they had their own place. And he believed that these elements tried to move towards their natural place. So earth being heavy, dry and cold, it sank to the bottom. So it was down here. Water was still heavy, but not as heavy as earth, so it sat on top. Then he knew that air was above the ground and above the water, so it was next. And that he could see fire would rise up, so he assumed that fire would sit on top. So that's the sort of way that the ancients perceived gravity. Right, so how does gravity fit in with the other fundamental forces of nature? So there are four fundamental forces of nature: the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. So this table arranges those forces in order of strength. And I've allocated the strong nuclear force to a strength of 1, just as a reference to the others. Right, so the strong force, it holds quarks together in hadrons. And a hadron is just like a proton or a neutron. They're not fundamental particles, they're actually composed of quarks. And the quarks are held together inside a proton by the strong nuclear force. It also combines nucleons together within a nucleus of an atom. So the protons are positively charged, and like charges want to repel. So the only thing stopping an atomic nucleus from flying apart is the strong nuclear force. And obviously, it has to be stronger than the electromagnetic force to hold the protons together. Now, with the other, it's like with the other forces, each of these forces has a carrier particle. Now, this is the particle that mediates the force, and it mediates it through an exchange of the carrier particle. So in the case of the strong nuclear force, the carrier particle is called the gluon, for obvious reasons. It glues the particles together. The strong nuclear force has an incredibly short range, 10 to the minus 15 meters. That is the scale of the nucleus of an atom. So beyond the nucleus of an atom, the strong nuclear force has no effect. Next, we have the electromagnetic force, which most of you are familiar with. It's the force responsible for electric and magnetic fields and electromagnetic radiation, like light and radio waves. Unlike the strong force, it has an infinite range. Like we can see clear across the universe, and we can see light coming from distant galaxies. So it has an infinite range. And it's about 1/100th the strength of the, 1/100th the strength of the strong force. And this carrier particle is the photon, which you've probably all heard of. And it occurs between charged particles. So like electrons, protons, because of the electric charge, that's where the photons are exchanged, and that's where it's felt. Next we have the weak nuclear force. This is the force that's responsible for atomic decay, and it can also transform particle types. It, like the strong nuclear force, has an incredibly short range, 10 to the minus 15 metres, so also about the size of the nucleus of an atom. It is considerably weaker, about 1/1,000,000 the strength of the strong force. And its carrier particles are the W and Z bosons, and it occurs between fermions. A fermion is basically a matter particle, like an electron or a proton or a neutron. They're all fermions. Then we come to gravity. Gravity, like the electromagnetic force, has an infinite range. It's felt clear across the universe. We can pick up gravity waves occurring from the collision of black holes billions of light years away. But it's an incredibly weak force. As you can see here, compared to the strong force, it's 10 to the minus 38. That's like comparing an atom to the size of the universe. That's the sort of scale we're looking at there. The carrier particle for gravity, the graviton, is a hypothetical particle because it's never been observed. One of the reasons it probably hasn't been observed is because gravity is such a weak force. It's almost impossible to detect it. And its appearance, it appears between all particles. So it's by far the weakest force, but on the universal scale, it's the dominant force. Right, so we go back to 1666, Sir Isaac Newton. He was self-isolating at his home because of the plague, the London plague. And the story goes, he was sitting under the apple tree and contemplating life, and he saw an apple fall. Whether it landed on his head, we're not too sure, but he saw the apple fall, and he made him think, what force caused the apple to fall to the ground? And this started him on a bit of a quest. It took him many years. He knew about the moon going around the Earth, obviously, and he realised that the force that caused the apple to fall to the ground was probably the same force that holds the moon in orbit around the Earth. And he was a very clever man. He was probably one of the most brilliant scientists of all times. He knew that the moon was 60 times further away than the radius of the Earth. So he worked out he knew the mass of the moon, he knew how fast it was travelling, he knew about Kepler's third law of planetary motion, and he worked out that the force of gravity at the moon was 3,600th the intensity that it was at the surface. So he knew that it must be obeying an inverse square law, and its intensity dropping off with distance. So he came up with the law of gravitation. Right, he didn't actually come up with this formula. He didn't know what the gravitational constant was, this G here. He didn't know what that was. So his law was more about the law of proportionality. So he knew that mass 1 multiplied by mass 2 divided by the distance between their centres squared equals the gravitational force. Right? But he didn't know what G was. Now G, the gravitational constant, as you can see there, it's an incredibly small number. It's got 10 to the minus 11 in it. The reason it is such a small number is because gravity is an incredibly weak force. And of all of the physical constants that we know of, the gravitational constant is the one we know with the least accuracy because it is such a small number. Action at a distance. This is a term he used because he could see that there was a force attracting objects together. But he could not see the mechanism that caused it. So he called it action at a distance, and it deeply troubled him. He could not see a physical means that gravity could transmit over empty space. And of course he never ever resolved that. And it was sometime later, in 1798, that a man named Henry Cavendish, he was an English physicist. He's also the man who discovered hydrogen, believe it or not. He was the first to derive a value for the gravitational constant. And it was a rather ingenious mechanism he used to do that. It was a torsion balance, and this is a model of it. And it's housed in a room to make sure that the air currents didn't affect it. Because basically what he was trying to do was measure the gravitational attraction between two lead weights. So he had the 160 kilo lead weights here, and then he had 1 kilo lead weights here and here. And by pulling these knobs here on these pulleys, you could spin this thing around and move these lead weights together. And then looking through a telescope, he would look at the deflection or the attraction between these spheres. And as you can imagine, it would be incredibly weak. But he did actually manage to measure it, and he came up with a value for the gravitational constant, which was reasonably accurate considering the time and the apparatus that he had. I did mention the inverse square law before. So this basically says that if you double the distance from the centre of the Earth, you'll have 1/4 of the gravitational strength. If you go to 3 times, it'll be 1/9. So this is the inverse square law. And electromagnetism, it obeys the same law. So the further away you get, the fainter the radiation becomes following the inverse square law. Now, the discovery of Neptune. So this was in the 1840s. So we had a French mathematician, Urbain Le Verrier, and a British astronomer, John Couch Adams. They independently calculated the position of Neptune using Newton's gravitational law by observing irregularities in the orbit of Uranus. So Uranus had been discovered sometime before, but when they plotted its orbit, they could see that it was being perturbed by something. And by using gravitational law, they calculated where a planet must be to cause those perturbations of the planet. Then a German, Johann Galle, he found the planet using the position calculated by the Verrier. He found it within 1 degree of the predicted position. So this was a bit of a triumph for mathematical astronomy. And it also validated Newton's law of gravity. But there was a problem. Mercury was a problem. So Newton's law of gravitation works remarkably well in calculating the orbits of the planets and the behaviour of most astronomical objects. It's also the prime mathematical foundation used to calculate trajectories for sending space probes to other planets. So it's a very successful law. However, in 1859, Le Verrier, the same guy who calculated where Neptune was, he noticed that Mercury's orbit precessed at a rate 43 arc seconds per century, which is not a lot, faster than predicted by Newtonian mechanics. So basically, every time Mercury went around the Sun, it would precess a little bit and slowly work its way around at 43 arc seconds per century, which is not a lot, but it is a measurable amount, and this could not be accounted for using Newton's law of gravitation. So, everything changed in 1915 when Albert Einstein published the general theory of relativity. Now, in this theory, it described gravity not as a force, but as the curvature of space and time in an object he called spacetime by mass. So presence of mass curves spacetime. Now, objects in motion follow straight lines in spacetime called geodesics. So the object thinks it's travelling in a straight line, but it's actually following a curved curved space-time like this. This is how sort of the moon orbits or a planet orbits the sun by following a geodesic through curved space-time. Now time is actually curved far more than the space is by mass, by a factor of c squared. C is the speed of light, so the speed of light squared is an enormous number. So time is curved far, far more than the space dimension by mass. And time slows down in a gravitational field. And I'll go into that a little bit more in a moment. Right, this is where it gets interesting and a bit heavy. Apologies. This is Albert Einstein's general relativity field equations. This is the general format of the equations. There are actually 10 of them, but they all look very similar to that. These values here, mu and nu, they're the Greek letters. That's these values here. They're a matrix of values of space-time coordinates, 1 of time and 3 of space. So if you imagine a matrix of 4 by 4 gives you 16 different equations, but they condense down to 10 because there's duplication. So that's how you get 10 equations, but they all pretty well look like that. So on the left-hand side, this tells matter how to curve space-time, and on the right side, this tells matter how to move through curved space-time. Apologies, there's one more slide on equations. So, these field equations are sort of equivalent to Newton's gravitational law, as long as the masses are small and the velocities are small. So if we're looking at masses like our everyday objects, they basically do the same result. And the velocities, this is where special relativity comes into it, not general relativity. Special relativity has to do with speed affecting time. So, and because time is what is affected most by mass in curved space-time, the velocities can have an effect as well. So the velocities are small, the masses are small, these two are pretty well equivalent. Right, so the first term is the Einstein tensor, and this represents the curvature of space-time. I know everyone's saying, what the hell's a tensor? I had to write this down. It's a mathematical object that generalizes scalars, vectors, and matrices to higher dimensions. Don't ask me to explain it any more than that, because I don't understand it myself. You also notice that both of these equations have g in them. Right? So g is the gravitational constant. So it does appear in Einstein's field equations as well. Now this is the Greek letter lambda, which is here. This is the cosmological constant. Now, in Einstein's original equations, this did not appear. And when he tried to solve his equations, and he had a lot of difficulty solving them because they were so complex, it showed that the universe was expanding. And back in 1915, everybody thought the universe was static. And, it's unchanging, it's always been there, it'll always be there, and it's just static. And the equations showed that it's actually expanding. And he thought, well, that can't be right. So he introduced the cosmological constant to force his equations to produce a static universe. About 10 years later, Edwin Hubble found that the universe was in fact expanding. And Einstein said that that was the biggest blunder of his life, so he promptly took lambda out of the out of his equations so that it would show that the universe was expanding. Then, fast forward to the 1990s, they found that the universe's expansion is actually accelerating due to dark energy. So then they had to put the cosmological constant back in again to account for that. And it's actually a small positive value to account for the acceleration of the expansion of the universe. So it represents the energy density of empty space or dark energy, which is what that is. The next term is the metric tensor, which designs the geometry of space-time. The next is the Einstein gravity constant, which scales the curvature to the matter present. And then finally we have the stress energy tensor, which describes the density and flux of energy and momentum in space-time. Have you got all that? It will be tested later. Right. Now, testing general relativity. So it's all very fine for Einstein to come up with his grand theories, but how do we actually test that it's correct? Well, when this theory is applied to the Mercury problem, it perfectly describes the precession in Mercury's orbit caused by space-time curvature around the Sun. So that was a good test for it. Then in 1919, light from a distant star was deflected around the eclipsed Sun by the amount predicted. And this was the topic of the talk from last month, actually. So, this is the real location of the star. And when we look at that, we can imagine the Sun being eclipsed, so we can actually see the stars. The star appears to be over here, because the light from the star has been bent around the Sun. And light being a massless energy, photons are massless, so they shouldn't be attracted by gravity because they have no mass. So the fact that the light has been bent around the Sun means that the light is travelling through curved space-time, not being affected by a gravitational field. So this was another test for general relativity, and the deflection was about what he predicted. Gravitational lensing. So this occurs when we have a foreground galaxy, like this giant elliptical galaxy here. And in the background is a spiral galaxy. But you can't see it because it's directly behind this galaxy. But the light from this galaxy is being bent around this galaxy through curved space. So we see it as a ring or an arc, and a magnified version of it as well. So they're also called the Einstein rings, and these occur quite often in deep space photographs, where we have not only a single galaxy, but even a cluster of galaxies bending light from far distant galaxies in the background. Then in the 1990s, Americans set up a probe called Gravity Probe B to test two of general relativity's predictions, and it confirmed these two predictions. The first was the geodesic effect, which describes how Earth warps space-time. So basically like this. And the second is the frame dragging effect. Because apparently when objects rotate, they actually drag space and time with them. Right? So they twist them up as they spin. So Gravity Probe B accurately confirmed both of these predictions. Just as a side note, Gravity Probe B contained the most perfect spheres ever made by man in the form of gyroscopes. And they were accurate to within 40 atoms of a perfect sphere. Now, I mentioned earlier that time passes slower in a gravitational field. So hopefully this graphic might sort of show how that happens. So here we have the Earth, which is bending space-time. So if you can imagine an object following this geodesic, and an object following this geodesic, this one's going to take longer to go from here to here, with a this one's going to go from here to here because the mass has bent and dilated time. Yeah. That's sort of a representation of how time dilation works. Now, the GPS satellites, which we all rely on every day, because they're outside of the Earth's gravitational field, or they experience far less than we do on the surface, their clocks tick faster than clocks on the Earth because of time dilation. And it's about 45 microseconds a day. You probably think, that doesn't matter much. But if it wasn't taken into account, the GPS system would go out of sync in about 10 days. So it has to be taken into account. But because the satellites are moving quite fast as well, we have to take special relativity into account as well. So we're gaining 45 microseconds a day due to general relativity, but we're losing 7 microseconds a day due to special relativity. So there's a net gain of about 38 microseconds a day, which has to be taken into account. And an interesting fact, the core of the Earth is 2.5 years younger than the surface of the Earth, because the core of the Earth is closer to the gravitational centre of the mass of the Earth. Right, now we go to black holes, is where it is there. Right, black hole gravity. Okay, so this is the most extreme example of space-time distortion. Right, so the escape velocity at the event horizon is the speed of light. So at the centre of a black hole is a singularity, which is where all the mass is concentrated. As you move out from the singularity, the further you get from the centre of mass, the escape velocity changes. So this is the velocity you have to achieve to completely escape an object. So the Earth has an escape velocity of about 25,000 miles per hour, something like that. So that's the speed you have to attain to escape the Earth's gravity. So at the event horizon of a black hole, the escape velocity is the speed of light. So that's why if you get closer to a black hole than the event horizon, you can never get out again, because you can't travel faster than the speed of light. Right? Because that's the cosmic speed limit. Now most black holes seem to have an accretion disk around it. Now this is a disk of material which is spiraling into the black hole. So that's this disk here, right? But the space-time distortion is so great that the accretion disk can be seen wrapped around the black hole. So that's the actual accretion disk from behind the black hole, but we can see it because it's been bent around it. So that we can see the entire accretion disk. And time dilation is so extreme that time actually freezes at the event horizon. Because as things are falling into the black hole, they actually hit almost the speed of light as they cross the event horizon, and time virtually freezes. So you can actually look at a black hole, it will look a bit like flypaper, where every object that's ever fallen into it will be stuck on it. As time slows down, and then stops, just as it hits the event horizon. But from the point of view of the object itself, it just falls straight through and gets crushed in the singularity. So it's all to do with relativity. And where if you're an observer from outside looking at it, or you're the actual object falling in. Right. Now, the equivalence principle. This is something that Einstein came up with. He postulated that it's impossible to differentiate between being in a gravitational field and a constant acceleration of 9.8 meters per second squared. So 9.8 meters per second squared, that's the acceleration due to gravity at the surface of the Earth, right? So, if you're in a rocket accelerating at that acceleration, and if Albert dropped the ball, right, it would appear to fall to the floor of the rocket, but it's not actually falling to the floor of the rocket at all. As soon as he lets go of it, it stops accelerating and the floor catches up with it. Right? But it's exactly equivalent if you're on the ground and you drop the ball. There was no way you could differentiate between these two situations. There's no experiment you can do that can differentiate between these two. Now, this is important, and you'll see as I go to the next slide why this is important. Right, now I do not suggest you try this at home, but if you jump off the roof of a building, what happens? As soon as you leave the roof of that building, you basically, gravity disappears, right? And if you had an accelerometer, if you were holding an accelerometer, right, it would measure 0 meters per second squared. So as soon as you jump off that building, you stop accelerating, right? And the accelerometer left on top of the building would be measuring 9.8 meters per second squared. But this poor chap here, he's looking down at the ground and he sees it accelerating towards him. So how is this possible if he's not accelerating? So it so happens that the surface of the Earth is accelerating upwards at 9.8 meters per second all the time. And that's how we perceive gravity. Right? We're not falling towards the Earth is pushing up underneath us. It's counterintuitive to what we believe, but that is what's happening. And it seems like the surface of the Earth needs to accelerate just to stay still in curved spacetime. It's like the Earth resisting the curvature of spacetime. And it's exactly equivalent to being in a rocket. Right? As soon as Albert let go of that ball, it stopped accelerating. And the guide is 0 meters per second squared, and the fall of the rocket accelerates upwards to catch up with it. This is exactly the same as if you jump off the building and you see the Earth accelerating up towards you until you hit it. Right, so let's have a look at the Newtonian view of gravity in a space-time diagram. Right, so here we have time in the vertical axis and space in the horizontal axis. And here's an apple. So the apple is just sitting on the ground. It's not moving through space, but it's moving through time. So we just have a line going straight up the graph. Make sense? Now, what happens if we put the surface of the Earth in the diagram? The surface of the Earth, just don't get us into the Newtonian view of gravity. Right? The surface of the Earth is not moving. Therefore, it's not moving through space, but it's moving through time. So now, what happens when we drop the apple? It falls to the ground. The curved line on this graph means that the object is accelerating. So the apple accelerates towards the ground until it hits the ground. So this is the Newtonian view of gravity. Right? Now, how do we look at the general relativity view of this? So now we have this situation. I said earlier that time is curved far more than space by mass. So you can see that the space axis is straight, but the time axis is bent. And you can see the timelines getting further and further apart as we get near the surface of the Earth, because of this time dilation. Now we have our apple. What happens when you drop the apple? Well, the apple's going to do that, because it's not moving through space. Right? But the surface of the Earth is accelerating up to meet it at this point here. So mass distorts time more than space, and the apple's moving through dilated time. So while the surface of the Earth is accelerating, the Earth isn't expanding. the upward acceleration of the ground is the ground resisting the curvature of space-time. Now, you can do this at home, and I did do this at home, exhibit A. If you cut that diagram out, which I did here, right, and you fold it into a truncated cone, now this is very small, right, you get something like that, right? So, and the Earth's over here. Now if you turn that sort of sideways, it looks like that, okay? So there we have the surface of the Earth over here, and you can see here that the time is being dilated as it gets closer to the surface of the Earth. So there's our apple, and it looks like that. So now it looks like the Newtonian view. And if you get this and you fold it over, you can see that the line that was straight before is now curved and looks like it's accelerating towards the ground. Right, now that all your heads are exploding, it gets worse. Quantum gravity. So there are two great pillars in physics, two great theories in physics, general relativity and quantum mechanics. And both these are enormously successful theories. General relativity, it works very, very well at the large scale. Right? Quantum mechanics is works very, very well at the very small scale, like the subatomic level. Right? But when it comes to gravity, the two theories are incompatible. Trying to describe gravity at the quantum level just doesn't work. I did struggle with this. So I will try and describe why that is the case. One reason is continuous versus discrete. So general relativity models gravity as the curvature of a smooth, continuous space-time, where quantum mechanics relies on discrete energy levels and particles. So when gravity is quantized, the equation produces infinite unphysical results. The nature of time. In quantum mechanics, time is universal and absolute parameter. In general relativity, time is measurable, relative, and part of the dynamic space-time. The problem is certainty. General relativity is a deterministic theory. So given the initial conditions of every particle in the universe, you can work out where they're all going to be in the future. But in quantum mechanics, it's probabilistic, right? It's dealing with uncertainties and superposition existing in multiple states simultaneously. So you can't predict where a particle is going to be in the future. And singularities. So I mentioned singularities before at the centre of black holes. So at the centre of a black hole, general relativity predicts infinite density and curvature, a singularity. Quantum mechanics forbids infinities and suggests our understanding of space breaks down before reaching that point, creating a fundamental contradiction. Don't ask me to explain it any more than that, because then we come to gravity waves. So Einstein predicted gravity waves, but he knew that they would be incredibly small, and he thought there would be no way we could ever be able to detect them. But the detect them we have. It was about 10 years ago, we managed to detect gravity waves. Now, gravity waves are produced when massive objects accelerate. Even just doing that, right? I'm producing gravity waves radiating out from my hand because it's accelerating through space. But you'd never ever be able to detect them. You have to have very massive objects accelerating to generate detectable gravity waves. So these are ripples in space-time that travel at the speed of light, and they were predicted by general relativity. But there is such incredibly small amplitude that only the most violent events in the universe, like black hole collisions, result in detectable events on Earth. So basically here there are two black holes in orbit around each other, and as they're orbiting each other, they're releasing a huge amount of gravitational energy, and because of that, they're spiraling in, getting closer and closer. And as they get closer and closer, they accelerate faster and faster, producing these gravity waves until they actually merge and then become a single black hole. So this is the LIGO detector. There's two of these in the US. They're a few thousand kilometres apart. It stands for Laser Interferometer Gravity Observatory. That's what LIGO stands for. And this is a huge facility. This is these two tunnels, 4 kilometres long. And basically the way it works is they fire a laser. It goes through a half silver mirror. So half of the energy is reflected up this tube, and the rest of it continues on this tube. Hits a mirror at the end, bounces back. The two beams are then recombined, and then go to a detector. Now, if no gravity waves are going through, the paths are identical, and the two waves will cancel out, and you'll get nothing, no wave. But if a gravity wave passes through this, it will change the length of one of these tunnels a fraction more than the other one. So when the laser energy is recombined, they'll be slightly out of phase. So we'll end up with an interference pattern. And that's basically how it detects gravity waves. But these gravity waves, they're so small, the amplitude of a gravity wave is about the size of a proton. So it's amazing they ever managed to detect these things at all. And because we've got two of these detectors several thousand kilometres apart, when they detect the event one, and there's a slight delay before it hits the other one, because these waves are travelling at the speed of light, they get a rough idea of where the wave's coming from. But also having two detectors sort of cancels out any local effects that might be misinterpreted as a gravity wave. Right, come to the summary. So general relativity tells us that gravity is not a force, but a curvature of space-time caused by the presence of mass. It is distinctly different from the other fundamental forces, and the elusive graviton will likely never be found. Gravity binds the universe together, and monumental events like black hole collisions result in gravitational waves that travel through the cosmos of ripples in space-time. Now, just before I go to the questions, I'd just like to say that I have a friend in the audience who's determined to stump me with a question on gravity. So in light of that, no questions